AHU.com. In this video, we're going to be looking at the VAV system to understand how it works, the main parts, and where we use them. VAV stands for variable air volume. This is a type of ventilation system which is commonly used in modern office buildings. The temperature of the supply air is kept constant, but the volume or flow rate of air supplied is varied. Variable air volume systems are far more energy efficient compared to its predecessor, the CAV or constant air volume system. VAV systems allow different areas or zones of a building to operate at different temperatures from the same ventilation system. This is ideal because not every room in a building will experience the same heat load. For example, one side of the building is in the sun while the other side is in the shade. One room might have just a few people with laptops, which produces a very small heat load, while other rooms may be filled with rows of racks of servers, each producing vast amounts of heat. With a VAV system, we can individually control the amount of cooling and possibly heating into each of the rooms, from the same main ductwork and the same main air handling unit. Here we have a model of a very small basic office. We have the main air handling unit in the mechanical room. Then we have the supply duct which runs through the building and branches out into each of the rooms. This supplies the fresh treated air throughout the building. On the other side we have the return duct. This collects all the dirty used air from the rooms and brings it back to the main air handling unit. Once the return air reaches the AHU, it can be rejected from the building out to atmosphere. Some designs of AHUs allow a portion of the return air to loop back into the supply stream. This will save a lot of energy. This recirculation of air is only used when conditions are right and where local laws permit this. But now, in a VAV system, the air leaving the AHU and being distributed throughout the building is being supplied at around 13 degrees Celsius or 55 degrees Fahrenheit. The fan within it, whether the temperature of the room is too hot, too cold, or just right. The VAV box will look something like this. There's an inlet, which is where the air enters from the branch and supply duct. Then we have the main VAV box, and then we have the exit where the air leaves and supplies the zone. Looking inside the VAV terminal, you can see it's a fairly simple design. There's nothing too complex happening inside these. On the side we usually find a controller, which is mounted onto the actuator. The actuator controls and rotates the shaft. Connected to the shaft is a damper. The damper is basically a sheet of metal. The damper can modulate its position to cover or uncover the inlet. This blocks the stream of air or allows it to flow, which therefore controls the flow of air into the unit and thus into the zone. When the room is too hot, the thermostat tells the controller to unblock the inlet and let more cold air in. When the room is too cold, the thermostat tells the controller to start partially blocking the inlet to prevent more cold air entering. The air entering the terminal is typically around 13 degrees Celsius or 55 degrees Fahrenheit, although this temperature can be adjusted by the BMS system or control panel on the AHU. If you want to learn how AHUs work, then we have covered that in detail in our previous video. Links can be found for that in the video description down below. Every terminal connected to this system will receive the same temperature air. Sometimes this air temperature is too cold, so we will often find an electrical reheater inside the VAV terminal which will switch on and warm that air up as it passes through. You don't necessarily have to have the reheater inside, but it's fairly common, especially in colder climates such as Europe and North America. The reheater battery doesn't necessarily have to be electric. It could also be fed from the hot water system or even a heat pump. But electrical heaters are most common because they are very simple to install in a duct. These then connect onto this cross shape. The cross shape is an airflow sensor. and it is basically measuring the change in pressure across the inlet. There will be a difference in air velocity between the center and outer regions of the inlet duct, because air flows faster in the center. By measuring the pressure at different points across the cross-sectional area, we can therefore calculate the average air velocity or the average flow rate into the VAV box. So how is this done? If you notice on the metal tubes, we have some holes. There are some on the front as well as the back of the tubes. Now, if you imagine the air is entering and colliding with the tube, and then it flows around it. So one side of the tube will be high pressure, while the other side is a lower pressure, thus giving us a pressure difference. Once we know the pressure difference and the size of the duct, we can use a mathematical formula, which is provided by the VAV terminal manufacturer, to calculate the average flow rate of air entering the VAV terminal, and thus, inside the electrical panel, we typically have the following components: the controller, the actuator, the pressure differential sensor, along with a small electrical transformer. The controller, actuator and pressure sensor can be separate items, but now it's most common to find these as an integrated unit, which makes installation as well as commissioning far more easier. The thermostat is connected to the controller, and this will provide the controller with information on the room temperature, etc. The controller is typically pre-programmed and will contain a strategy which tells the actuator a small internal motor in the actuator rotates this, which results in the shaft, thus the damper, changing position. Additionally, the controller usually allows for network control or to link to other terminal units also. The damper doesn't usually fully close. That's because we still need a certain amount of fresh air to enter the room. So it partially closes, which allows a small stream of air to trickle past into the room. If the thermostat detects that the room temperature has increased above the desired set point temperature, then the damper is instructed to open further and allow the cold air to enter. Remember, this air is around 13 degrees Celsius or 55 degrees Fahrenheit, so that will cool the room down fairly quickly, and the warm air will be sucked away through the return duct. For example, in the middle of summer, when there is a maximum solar gain, perhaps a busy room full of people and computers, so we have the maximum heat load, the damper will therefore be 100% open to let as much cold air in as possible and remove the unwanted heat. During the peak of winter, or even on a normal cloudy day, when the room is empty and there isn't much heat load, the damper's position will be further towards the closed position to minimize the cooling but still allow fresh air to circulate. You can get fan-assisted VAV boxes. There are many variations, but this is a simple example. It's essentially the same as a regular VAV terminal, except we have this extra section which usually contains a small filter and a fan. The fan allows air to be pulled in from the room. This air is dirty, so we pass it through the filter to stop the dust from collecting inside the fan, the ductwork, or even the heating element. This air will enter through the side of the unit and then mix with the main airstream as the damper opens. This is beneficial because we can reduce the heating demand on the reheat coil because we are reusing the heat that already exists in the zone. This also ensures a constant volume through the unit. So as the dampers open and close, we don't get surges of air flowing into the space, but by using the fan, we can maintain a constant turnover of air within the room. Additionally, it also reduces the chances of cold air being dumped out through the diffuser and onto anyone sitting below it, which wouldn't be very comfortable. So, to avoid all of these problems, we can sometimes use a fan-assisted unit. Now, if you imagine that all of these VAV terminals are connected to the same system, and they can all open and close to suit the cooling load of their individual zones, then obviously we're going to get a large pressure fluctuation in the main ductwork. If we left the fan to run at a constant speed, then when most of the VAV terminals are fully open, the fan isn't going to be supplying enough air. And if they all close, then the fan is going to be supplying too much air. The pressure in the ductwork is going to therefore fluctuate as units modulate their damper's position. So, what we need to do is fit a pressure sensor towards the furthest point of the ductwork. This pressure sensor is connected to the VFD, detecting the pressure at the furthest point in the system. We choose this point because it has the largest pressure drop of the entire system due to the frictional losses in the ductwork. We determine the minimum allowable pressure at this point. Basically, this is the pressure that the furthest VAV terminal can sufficiently operate at. The VFD varies the speed of the fan to increase or decrease the airflow rate and thus the pressure in the ductwork. It does this to try and ensure the pressure at the furthest point remains within limit. If this furthest VAV terminal can operate with sufficient air pressure, then the rest of the system can also. This control strategy therefore allows the fans to run at optimal speeds, which will therefore depend on them. By the way, we have covered how variable frequency drives work in great detail in our previous video. Do check that out, links can be found in the video description down below. Okay, that's it for this